Hello, Numa. So, formulae, formulae of ionic compound, right? This is the subject. So, first, let's just understand what this is. Ionic compound. What is this? An ionic compound. So, let's break down the word, the phrase. So, a compound is two or more atoms that are chemically bonded. And an ion or ionic here means the it means anything to do with ions, really, not electrostatic. Now, breaking this down, this roughly translates to a compound formed. So a compound, which is here, a compound formed via ions. We can write it as is the positive and negative. Let's make this one. Ions attracting each other to form a compound. Or you could also write form a bond and ionic bond. Right? Okay. So examples are calcium oxide. This is fine. Then you have calcium chloride. If we did calcium chloride, it would be CaCl2. So these are the different formulas of ionic compounds, right? And there's also polyatomic ions, but I'll get into that later. But first, to understand why the formula is like this, let's first see how an ionic compound is formed. Okay, so let's say, for example, magnesium oxide. Magnesium oxide, right? So if you look at the periodic table, magnesium has an atomic number of 12. Oxygen has an atomic number of 8. So let's write this. 12 oxygen. Oxide means oxygen, so 8. So if we let's get an atom. So magnesium will have 8 protons. Make the font bigger. So magnesium will have 12 protons. Oxygen will have 8 protons. So, and the electronic configuration of atoms, the electronic configuration, which is essentially how the electrons, because an electron always has the same number, an atom always has the same number of electrons as its protons. So how these electrons are arranged, and electrons are arranged into shells, orbits, or orbits, whichever term you prefer. But the how many there are in each shell or orbit is maintained through this electronic configuration. This is for all atoms. 2, 8, 8. 18, and it goes on, it goes 18, then 32, but we don't need that much. So this was our magnesium. So first shell 2, so, and you can only have up to 2 in the first shell. The second shell 8, so that'll make 10. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2, 10. And then in the last shell, we have 2 more left. So 2. So magnesium's electronic structure is essentially this. It has 2 out of 2 in the first shell, 8 out of 8 in the second shell, but only 2 out of 8 in the last shell. It can, any atom can have up to 8 in the third shell, but magnesium only has 2 out of 8 out of 8, right? Now oxygen, let's draw oxygen. So oxygen, I don't think we'll need a third shell for oxygen, so 2 in the first shell, and then 6. We have 6 electrons left. So 1, 2, 3, 4, 5, 6. Yeah. So we don't need a third shell. So this is oxygen structure, which is going to be 2 and 6. This is 2 out of 2 and 6 out of 8. So what happens during ionic bonds is first these this metal and a non-metal, they form ions, right? So what an atom tries to do is it tries to fulfill its outer shell, its electronic its out the last shell. So for this for the magnesium, it's this one, this shell, and for oxygen, it's this shell. What it tries to do is it tries to ensure that uh, the atom is completely saturated. And what metals do is it's easier for the metal to get rid of it's easier for the metal to get rid of these two electrons, and then it becomes stable. It has complete electronic shells. And what oxygen does, it's easier for this oxygen to get 2 electrons from somewhere. So from here. And then once they take it, XX becomes plus 2 equals 8 out of 8. So the oxygen becomes stable. Its electronic configuration is fulfilled, it's satisfied. But in the process of doing this, you'll notice that metals lose the electrons they were originally carrying. So for magnesium, since magnesium has 2 extra electrons in its outer shell, it'll have the ion that magnesium will form will be Mg2 plus, because there's 2 more protons than electrons. And oxygen, since it's gaining 2 electrons, it'll form the ion MO2 minus, because there's 2 more electrons than there were originally right? So there's 8 protons and there were originally 8 electrons, so this was stable. 8 and minus 8 cancel each other out, but then you got 2 electrons to fulfill the outer shell, so it becomes 2 minus. And so an atom, when it has a charge, so when it has lost or gained electrons, it becomes an ion, right? Okay. So what I've shown you is the process through how this ion forms, but the ionic bond, let me draw that for magnesium and oxygen. Okay, to look at this. Oxygen, we do not need a third shell, so get rid of that. Uh, okay, so 12 is at 8 equals, so 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then, of course, when it became an ion, it lost the two shells in its, these two shells went over there to another atom, which is a nonmetal, because nonmetals will accept electrons and metals will lose electrons. So these two electrons went to the nonmetal, so it doesn't have an outer shell anymore. And for oxygen, it never had an outer shell to begin with, but because 5, 6, and then it got these from the, there. So that's a magnesium ion. So this over here has a 2 minus charge. It's 2 less electrons than what it originally had. And this is a, sorry, this is 2 plus, 2 less electrons, so 2 more protons. And this is 2 minus because it's got 2 more electrons. So these 2 plus and this these charges, this positive charge on the from the magnesium ion and the negative charge from the oxygen ion, these result in the ionic bond that is formed. The atoms, what they do is they stick very close to each other. They don't share bonds like they do in covalent compounds, but they stay very close to each other, and that creates this is the bond that is created through the charge. Okay, so I think we have a fair idea of what an ionic bond is and how this is formed. Now, let's move on to formulae. So, you'll notice that over here, this magnesium and oxygen ion, they both have a 2 charge. Magnesium has 2 plus and oxygen has 2 minus. So for an ionic bond to happen, for an ionic bond to take place, the charges must equal to 0. So over here, this automatically happened. Magnesium had a 2 plus charge, oxygen had a 2 minus charge. But say this was calcium chloride. Okay, and I haven't put the formula in yet, but calcium, let me move this. Calcium has, we can easily know the charge of an atom by looking at the valency, right? So calcium has a valency of 2. Okay. I can't mark it. Hold on. Okay. Okay. So calcium has a valency of 2. So metals always lose electrons and they become positive ions. So this basically means when a calcium ion is formed, we can just use the valency to understand the charge on the ion. So calcium will become a 2 plus ion, and fluorine, so fluoride, so over here, has a valency of 1. So chlorine, because it will always gain an electron, will always be a negative ion. So it'll be a chlorine ion will always be Cl. It'll always be Cl1 minus. Okay, and calcium will always be Ca2 plus. Is going to lose 2 electrons. So for an ionic bond to take place, as I've said earlier, the charges must equal to 0. So calcium we know has a 2 plus. Chlorine, on the other hand, has only 1 minus. But this is a bit of a contradiction, isn't it? Because we need these to equal to 0. This needs to equal to 0 for an ionic bond to take place. Otherwise, the calcium will still have, you could do plus minus, but then calcium would still have a 1 plus charge, which would attract something else. So how this compound is formed is basically what we do is we multiply, basically we try to get these two numbers common. So if we had 2 chlorines, let's multiply this 1 minus, the chlorine ion would be 1 minus. Then what would happen is the calcium stays same. This chlorine, this becomes 2 minus now, right? So 2 plus minus equals to 0. This does not equal to 0, is unequal to 0. But when we multiplied this by 2, this became 0. So this is one method of finding the formulae, right? So 2 minus. So because we have to multiply this 2 over here, we just put the 2 for chlorine. And this is one method. The other method, and I'll show the other method, which is the method Sir has taught. It's the dropping method. You just, calcium has 2, chlorine has 1. You drop this, you drop that. Calcium stays 1, chlorine becomes 2. And you'll see this is consistent with this. This is consistent with this. But this is basically, this process is a shortcut. And therefore you'll sometimes have to simplify this, but this method you won't ever have to simplify. I'm going to show why in a second. So that's calcium. Let's do another example. Let's try let's do lithium oxide. So Li and oxygen. Let's not worry about the number of atoms now. So let's look at the valency chart. So lithium has a valency of 1 over here, and oxygen has a valency of 2. So because this has a valency of 1, the lithium will always get rid of 1 electron, and then it'll become Li plus proton, and not proton, an ion. And oxygen will become, and since it will always gain 2 electrons, it'll become 2O2 minus. So what's going to happen this time? Let's make the lithium blue, oxygen red. So 1 plus, and then 2 minus. Okay, And so we can see this is equal to 0. Equal to 0. Because we have 2 minus here, but we have 1 plus here. We'll be left with 1 minus charge from the oxygen. So what can we do? We multiply this into 2. Then we get 2 plus charge and 2 minus charge, and will result with 0. So the atoms will attract to each other, and the compound will be formed. And because we put the 2 here, we multiplied this ion, this positive ion, into 2 for this to become neutral. We just put Li2. Oh, okay. Now let's if you did it with the valency method, this would come with the same result. Let me show. Let's do one variable valency. So these are what are variable valencies? Where did they come from? So they come from these things. Let me change my color. So lead, copper, iron, silver sometimes, but here it's not mentioned. Manganese, chromium. See, there's commas beside their valencies in this chart. This is because they're not in group 1 or 2. They're over here. These are transition metals. And the problem with transition metals is we saw in this original example that magnesium just loses the electrons in its outer shell. What these atoms do is they'll also sometimes lose an extra electron. Imagine this was a transition element. They will also sometimes get rid of these electrons as well. So this is why they have variable valencies. In different environments, under different conditions, they will lose different electrons, a different number of electrons. So they will sometimes form this and that. So what we do to represent them, we write them, let's say for our example, our compound is lead oxide. Lead oxide, and let's say this is lead IV oxide. So what this means is IV is Roman numerals for 4, and this means that the lead has a valency of 4. So the ion this will form will have a 4 plus charge. It will lose 4 electrons. So lead IV oxide. This is an ionic compound. Okay, let's mark lead in blue and oxide in red. So LiO. Actually, you should also write the IV. Oh, so how do we find the formulae? Mark this blue, mark this red. Okay, so, oh, wait, hold on. I just wrote lithium. This should be lead. My bad. Pb. Okay, so we know that this has a valency of 4, so it'll get rid of 4 electrons, and thus it'll have 4 more protons than electrons, so a 4 plus charge. Oxygen, we know, has a valency of 2, and it'll gain the 2 electrons from another metal, so it'll have a 2 minus charge. 2 minus charge. Now, here, what can we do for this? Is all we can see. This is unequal to 0. So what can we do? We can multiply this 2 minus, and then we get 4 minus and 4 plus, and this will be equal to 0. Okay, so because we took 2 oxygens, this will be PbIvO2. Now, if you did this, so the method we've done is we've just taken what ion it will be, and we've we found the lowest common factor here, right? We found the lowest common factor here, and then we've because the lowest common factor between 4 and 2 is not the lowest common factor, the lowest common multiple. 4 ones are 4, 2 twos are 4. So we just find the lowest common multiple and we multiply whatever we need to for the lowest common multiple to take place. For 4, it was just 4 into 1, so we didn't show that. And for 2, it was 2 into 2. If you did this method with the cross and drop method, which would be like this, right? It will be like 4 and then 2, and then you would drop this here, drop that there. So you would have PB2 and O4, and this would become, we would simplify this to PBO2. But the reason we have to simplify this here is this cross and drop method. What it's doing is it's performing a shortcut. This cross and drop method, what it does is whatever the ions are. So here we have 4 and 2. It just multiplies this into these two numbers, and it gets this result. And this is always a common multiple. This will always be a common multiple between the two numbers because you've just multiplied them with the two numbers, right? So you see, you need two. You need two 4. You need two 4 plus ions to make this 8, and you need 4 2 plus ions, which is what we originally got, to make the 8. So this is what the drop and cross and drop method does, and that's why you have to simplify it. If we the way we've done it, we found the lowest common multiple. Sometimes by doing this method, you get the lowest common multiple, but as I've shown in this example, this is not always the case. Over here, we found the lowest common multiple by just taking it as 4. What this method does is it takes the common multiple as the product of these two numbers. And they will always be a common multiple, but they may not be the lowest common multiple. This is why this arises, which is why you have to simplify this. So it's up to you which method you want to follow, but that's what it does essentially. You just multiply 2, and you multiply this by 4. That's why you end up with that's why you end up with since I've written that, they took the LCM. The LCM was 8, remember? So I'm just showing how this worked. So you had 4. This was 4 plus, and you had 2 minus, and if you drop it at the end, it becomes PB2 before simplification. But why this is because, as I said, they did 4 into 2 equals to 8. So they multiply these two numbers to get a common multiple. So what do you need to multiply with 4 to get 8? You just need to multiply 2, and 2 you just need to multiply 4. And because they've multiplied these two numbers, obviously the multiple that we've taken is literally for each number, it's just always going to be this, and for the common multiple for this number is always going to be this. That's why you can just do drop and cross. But as I've shown, you need to simplify this. BB over 2. 2 is to 4, so 1 is to 2. Okay. I hope that's illuminating. Now, you've seen just the general formula. You've seen variable valency, regular ionic bonds, those with variable valencies. Now, sometimes we'll also see polyatomic ions. Okay, and what these are is I've drawn this. So this is a sulfate ion. Okay. And what these are these are all nonmetals. These are all compounds of nonmetals. Okay. And they're ions because I'll just show in this example over here. Let me enlarge it. They don't bond completely. Okay. If you looked at carbon dioxide, these are nonmetals, so they have to bond covalently, right? So carbon dioxide, what happens is uh, carbon, how many electrons? Yes, 4 electrons in its valence shell, right? Carbon, 3, 4, and then it's dark for carbon dioxide. Oxygen has 6 in its valence shell, so 2 oxygens. They end up sharing with the carbons. They form 2 double bonds. This is O, this is O. I haven't drawn the electrons in between. So there are 4 here. 2, 3, 4, 2, 3, 4. And so the electron shells of both of these atoms become fulfilled because you see here, carbon has 4 here and 4 here, so it becomes 8. And by sharing, oxygen gets 8 here, and this oxygen gets 8 here, so the formula becomes CO2. And this formula has nothing to do with valency or anything. For nonmetals, it's just whatever the formula says, that's the amount of atoms there are. And you can't figure out the formulae of covalent compounds. You can only figure out the ionic ones. You can't use valency to figure out covalent compounds because as I'll show here, what happens here in this polyatomic ion, so there's sulfur and there's 4 oxygens, right? So what happened is this oxygen, it did a double bond over here. There's another oxygen that did a double bond over here. And this oxygen did a single bond, and this oxygen did a single bond. So what happened was these, I don't know if you can see, but this electron was left unpaired, and this electron was also left unpaired. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So when this compound formed, not all the there wasn't an equal number of electrons to protons after the sharing is done, which is why this got a 2 minus charge. As you can see, sulfate, SO4 2 minus. So this is why polyatomic ions have these charges. Their covalent bonds, the covalent bonds were not able to completely fulfill their outer shells. So and so these basically become ions because they have charges and they stay together. They're polyatomic. Poly means many, atomic means multiple ions, so they become polyatomic. And so let's take an example. Let's take NO3 nitrate, right? So this has -1 charge. The one we can't see is we don't generally write it. NO3. 3 is just the amount of oxygen. Don't think that's the charge. The charge is -1. So if that is -1, let's say we had, actually let's do a little something more interesting. Let's take phosphate, PO4 3 minus. So that's 3 minus charge, and let's take something that has, let's take manganese 7. Okay, let's take manganese 7, and let's take manganese VII phosphate. I think I could also just do it closer. Put it here. I forgot the. Okay, I'll just write Mn. I forgot the formula for manganese, but I'll write Mn for now, just for explanatory purposes. So manganese VII, which is 7, and then phosphate. The formula for phosphate was PO4, PO4. Phosphate. So let's make this blue and this red. So manganese VII means this will be 7 plus, and phosphate we know has a valency of 3, it has a charge 3 minus. So the lowest common multiple I can see is 21. 7 3s are 21. We can't really get anything else in between, so what we have to do is multiply this with 3 and this with 7. So what we're doing is literally the drop and cross method. So you could write MNVII 3 and write this in brackets. It should be 8, 4, 7. Right, because this is a polyatomic ion, you have to isolate it. Otherwise, this just becomes oxygen. If you wrote like this doesn't make sense. Why is there 4 and there 7 after? Okay, and what I've done is just the drop and cross method, because you'll see we'll multiply for the lowest common multiple. It's just the two numbers multiplied. The two numbers 7 and 3 multiplied makes the lowest common multiple. If you want to see, we do with 21 plus 21 minus equals to 0. If you did drop and cross, that would be, so VII is 7 here, and there was 3 there, drop, cross. Okay, and we can't simplify this further. 7 is a prime number, so this stays. And this is an example of the drop and cross method being the lowest common multiple. But as you've seen before, this is not always the case, which is why you sometimes have to simplify the drop and cross method, but that's not a big hassle. It depends on you which method you prefer. And that is ionic formulas. Okay, that is how you write ionic formulas. That is how we make ionic formulas. The formulae for ionic compounds.